The next speaker will be Seok Kim, Black Holes from Anomalies.
We're talking about the properties of black holes in AES, which you can derive or constrain from conformal field theories in the AES theory. Most importantly, the role of two anomalies in the CFT clinical control, and other techniques that are used will be some background effective and so on. Well, I'll eventually get to some physics of black hole, but the main interest of mine today is just the high temperature partition function of conformal field theories, which are radially quantized. So using conformal field theory, there's a canonical method of putting this system on spatial sphere times temporal line. And I want to study the high temperature partition functions of this conformal field theory on this manifold. So in the Euclidean field theory setup, you're led to consider the quantum field theory on the sphere, same sphere, times the temporal circle, where the circumference of beta is the inverse temperature. And I want to study the high temperature in the sense that this beta is much smaller than the mass scale set by the sphere radius. And eventually, what I'd like to seek for is to seek for a higher dimensional version of the famous two-dimensional Cardi formula between the CFTs. So we know that torus partition function of conformal field theory is S1 times S1 has a characteristic higher temperature behavior constrained by conformal symmetry completely. So if you take this chemical potential, inverse temperature is small, free energy is given by central charge divided by this beta-like parameter. So we call this Cardi formula. Something like that couldn't be found with higher dimensional CFTs just because conformal field theory conformal symmetry is much weaker. But still, I call the leading high temperature behavior of log Z as my Cardi free energy. The divergent term as we take beta to be 0, and maybe keeping some other chemical electric charges, angular velocity for the spin, and so on. So conceptually thinking, this high temperature limit of the free energy can be decomposed into two parts. Firstly, one can consider the contribution for the zero modes carrying no colors applying momentum on the small circle. For this first part, you have to consider the path integral of the quantum field theory in one lower dimension. In the standard thermal partition function, they are absent due to various mass terms generated. If you do the radial quantization, so let's say for scalar, there are conformal masses, conversion coupling generated. For fermions in the antiperiodic boundary condition, they also have large masses generated. So in the ordinary partition function, they are absent. I'll be soon discussing supersymmetric quantum field theory and some within indices. There, this kind of zero mode can arise, but it's quite obvious that they cannot contribute to the divergent part when beta is set to be 0, because they are not sensitive to this Q-first of the small circle, almost by the definition of zero mode. The part which will be more important in my talk is the effect coming by integrating out the infinite power of heavy Hertz-Klein modes on this circle. This really contains information about the divergent leading path of the free energy at high temperature limit. So this part will be my main concern. The part of the free energy which is carrying inverse, which are inversely proportional to beta, which are carrying negative powers of betas. So these Hertz-Klein modes contributions can be in the in the one lower dimensional perspective, can be all encoded in the effective actions of various background fields, where the background fields are encoding the information about the chemical potentials of this partition function. So for instance, if you're interested in four-dimensional CFTs, the divergent contribution from Hertz-Klein modes can be neatly written as some effective actions of background fields on free sphere. There are various background fields depending on what your problem is, but the universally appearing part is obviously the metric on, let's say, the free sphere. If you have angular momentum, the metric could be squashed. There could be background vector fields and scalars, various sorts. The canonical vector and scalar field that appear is appearing, it can be seen if you reduce this higher dimensional metric in the Karusa-Klein reduction form. So the radius square of the small circle, temperature-like variables, that's called the dilaton. The off-diagonal metric appearing here are called drag photon. They're universal scalars and vectors, and that could be more, depending on which flavor symmetry you have and so on. So in conformal field theory, we have no intrinsic scale parameters. So you have two dimensional parameters. One is the radius scale of the circle, another is the radius scale of the sphere. So in any partition function, they should make a dimensionless combination, beta divided by r. So you can really see that the small beta, high temperature expansion, is a 1/r expansion. And from the three spheres effective action viewpoint, they will be making a derivative action of background field. So I've shown a few lowest order terms of this universal background fields in the derivative action, and this dot 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 implies that there can increasingly be infinite power of contribution arranged in derivative expansion. So the leading term basically has no derivative. So we formally call it cosmological constant terms of background fields. The next two leading order terms can be either Einstein-Hilbert term, two derivative, or the Bragg-Gordon kinetic term, and there's also a dilaton kinetic term, but in my problems, I won't never use dilaton kinetic term. They'll turn out to be all vanishing. So these are some lowest leading and next leading order terms. And the coefficients of these derivative expansions, of course, depends on coupling constant. So if you want to study that strong coupling, these are all really unknown. Unless you can really use the strong coupling path into the four-dimensional theory. So these are very difficult to compute, coupling dependent. However, in this derivative expansion, there are specific finite number of terms, called Chern-Simons terms, on odd-dimensional sphere, if our underlying field theory is even-dimensional, which are coupling independent because of this background, large gauge transmission, and so on. And since these are coupling independent, you might hope that you will be able to determine these coefficients by basic kinematic consideration. And indeed, it will turn out to be true, as I'll illustrate to you later, that the toothed anomalies of the global symmetries in your system can completely determine a subset of terms in this derivative expansion. That's good. However, in the normal partition function, they turn out to be sub-leading terms, next leading or next leading or so on, in this normal derivative expansion. So you don't, if you're interested in the real leading part of the free energies, you can't really compute it because they are unknowns, but you can compute some sub-dominant terms, completely dictated by anomalies and so on. So these are the structures, salient structures of background field expansion, encoding the contributions from these heavy Karusa-Klein laws integrating out. So for instance, if you consider a strong coupling conformal field theory, large N, which has ADS dual, these expansion structures, despite you have various unknown coefficients, these structures should be compatible with the thermodynamics of ADS black holes in the gravity dual. It's high temperature means that you're eventually considering a black hole with large mass and so on, large charges and so on. Or for instance, with large working temperature in generic cases. So these kind of structures at least should constrain the thermodynamics of the pure large black holes. So let me, before getting into more quantitative details, let me explain to you that with a very simple example. You can really do Schwarzschild black holes, but let me be a little bit more general. Let me consider curved black holes in ADS 5, which can be studied using certain four-dimensional series. And the charges that we are interested in are energy and two angular momenta on free sphere. And these all have their dual chemical potential. So the energy is conjugated to temperature, and the inverse temperature is nothing but the circumference of this tau circle, shifted by beta. The angular momentum chemical potential can be realized as twisting the two angle variables of free sphere by the time coordinate, where omega is the angular velocities. And you can rearrange these four-dimensional metric, expanding the complete sphere and recollecting them so that you can represent it as three-dimensional Karusa-Klein field. This complicated mass is a three-dimensional Schwarzschild metric. This profile, after you recombine the complete sphere, is a dilaton. This is a Bragg photon, all depending on angular momentum and temperature parameter of the complicated matter. So you can plug these values in. In the effective action that I illustrated to you, these are the leading next to leading order, unknown coefficient. But anyway, you can evaluate the functional forms. You can see how it depends on betas and omega. It severely constrains the form of the high temperature effective action. with unknown coefficients. So these are the free energy. And if you do the Legendre transformation, this will eventually turn out to be entropy. So these are the first few terms appearing in the derivative expansion form. For simplicity, I have kept two angular momentum to be the same. In principle, you can do more general computation. Omega 1 to cap. So there are three unknowns if you're interested in the leading and next leading order contribution. And these will have direct consequences on the properties of large per ADS black holes. If you consider the leading order, it will almost behave like a black brain, and the next leading order is one of the charge effects. So to see really the consequences, you take this equation, and you can get two other equations by performing the Legendre transformation with two chemical potentials. You extremize with beta, extremize with omega, you get two more equations. You get three equations for S, E, and J. You solve for this in terms of chemical potential. You get an expansion, expanding E, J, and S in terms of these unknown variables. Okay? But still, they have very non-trivial functional forms constrained by these effective vector structures. So just by fitting these three parameters, we can non-trivially reproduce the thermodynamic quantities of curved black holes in ADS5. So these are the expressions for curved black holes. The divergent parts are equal parts, which can be completely reproduced by just fitting three coefficients. So you cannot really completely predict or explain the properties of curved black holes because strong coupling calculation is difficult. But still, this is fairly impressive. Just by these kinematic considerations, you can explain many parts of these curved black holes, like the functional forms and how. This is good. Any questions so far?
What is the meaning of
Small.
this?
Small a is just rewriting. Okay, so omega is introduced as dimensionless variable, and small omegas. Capital omega, there's a couple, so it's beta times omega 1, beta times omega 2, so it's a quantity having dimension of length. It's just a rewriting of omega in a dimensionless unit. And I do so because A is the angular velocity parameter, which frequently appears in these curved black hole solutions. So it's just a parameter match between the chemical potentials and the black hole parameter.
This terms vanish.
Which term vanish? Sorry.
Is it from reason this EJS type divergent it was one?
Oh, it's a It's a limit with yeah. There's a reason why it diverges. It's so roughly speaking, angular momentum is weighting the states with J. Beta is weighting the states with energy. And if you consider in the language of conformal field theory, operators are addressed by derivatives, right? And the derivative carries one spin and one angular momentum. But if beta is taken equal to omega, certain derivative gets just weight 1 in the partition function. But operators can be addressed by an infinite number of derivatives, and if they are not suppressed, the partition function diverges. Something like high temperature, strict high temperature limit with angular momentum also built in. So beta minus omega and beta plus omega are both playing the role of temperature-like variables, inverse temperature-like variables. So that if you take any of them 0, the partition function just shows a high temperature divergence. Any other questions? So I think so far the studies are quite interesting. But you can do a much more quantitative studies. Beyond just constraining the high temperature partition function and constraining the black hole free thermodynamics. The similar kind of calculus can be done for what is called an index. So index is the same partition function, let's say of S3 times R, but with suitably defined -1 to the Feynman number of factors and chemical potential. So it only requires contribution from BPS states in supersymmetric conformal field theories. And these partition functions are generally expected to be independent of continuous coupling constants. So all these coupling-dependent coefficients are just expected to be not appearing. Okay? So if you consider the index version of this partition function at high temperature-like chemical potential, well, corresponding to the large size of black holes, you expect that these unpredictable terms will be automatically somehow disappearing, while these robust terms, independent of coupling, should be the dominant contribution. Okay? So the predictive power of this method becomes much more powerful. So let me just briefly explain what the index is. Normally, index is defined over trace over BPS equal space with -1 to the fermions inserted. Let me treat it in a slightly different way. So a superconformal field theory in 4 dimension can have BPS operators, some local operators, weighted by their angular momentums carried by the operators. There are 2 chemical potentials. And also there's a U1 superconformal R symmetry whose chemical potentials are denoted by delta. And if these deltas and omegas satisfy this relation, it's supposed to be counting contributions from BPS operators only, and it's independent of complex master. There is standard factor of -1 to the fermion number, which I absorbed into definition of the chemical potential. So if you plug in the expression for delta or omegas, eliminating one of these 3 variables, the exponential of 2 pi I times some spinor-like charge will appear, which automatically plays the role of -1 to the fermion number. So with this, it becomes the index. I can still introduce a formal inverse temperature-like variable, conjugate E, but with this this charge combination, so that E minus this combination of charge becomes square of the supercharge. So following the standard argument of between index, beta formally plays the role of inverse temperature, but it's a fake parameter. The index doesn't depend on beta. So I should just keep this as a regulator, which you can take to a convenient value for the computation. It turns out that the computation is very easy in our background field formalism if you take it to be very, very small. So it formally plays a role until a certain stage as a small inverse temperature-like parameter, but you should remember that it's a fake parameter. Nothing should depend on beta. Okay? And if you take a careful look, the real parameter, which should play the role of the small derivative expansion parameter, are the small angular velocity parameter for the rotations. Intuitively, it comes because the energy of the BPS operators increases if you increase the spin. So large spin plays the role of large energy. So small omega will play the role of going to the region with large mass. If you take a look at the Dilaton field, formally many fields are just singular in this small regulated parameter. But that's a fake. If you insert these into the effective action and do the integration, beta dependence is somehow guaranteed to vanish if you're doing this next. So this one over beta dependence somehow should cancel with other terms and they also go away. And assuming that, the leading term which is giving rise to the small radius, small effective radius of a compactification will be the angular momentum velocity, angular momentum chemical potential. So small omega is really playing the role of the dominant the expansion parameter of the derivative. And since we expect certain apparently leading cosmological constant term and so on to be not appearing in the index because they're coupling dependent, we expect some reordering of naive derivative expansion such that Chern-Simons term will be the leading term. Indeed, that turns out to be the case. The background fields are following. The metric, Dilaton, Greiff-Orton are just the same as before, up to a small shifts by regulators. And since you have superconformal R symmetry and maybe other flavor symmetries optionally, there are some background 3-dimensional gauge fields and the holonomy scalar fields coming from the chemical potential for these symmetries. And as expected, we evaluate all the non-Chern-Simons terms in our scaling limit when regulator is taken to be 0. All the terms are just vanishing, the beta going to 0 limit. This used to be the leading term in the ordinary partial function, which apparently has the leading power in 1 over beta, small beta. But if you plug in all these singular fields and evaluate, they turn out to be subgroups, as expected. You just check this, and all the terms for Chern-Simons term get positive suppression factors. That if you can determine the coefficients, the finite number of Chern-Simons terms, you can get the high temperature tardy leading behavior of the index, almost for free.
So this is fixed omega.
Huh?
Omega is fixed.
Omega is small but fixed. Yes. Yeah. Beta is a parameter which you just take to 0 as a limit. Omega is a small but fixed parameter, which is the expansion parameter of particle energy. So I'll be also interested in subleading corrections in omega. You might get confused with these poles and so on, but there are good interpretations of that, and you can just ignore the pole and just take beta to 0. There are good interpretations of that, which I can bring later. Chern-Simons coefficient as I advertised earlier, have been determined once you know the anomaly structures. So let's say for the 4-dimensional conformal field. So there turn out to be two distinctive Chern-Simons terms. One is the usual gauge invariant Chern-Simons term for background field that you know. I showed you in the previous slides the Chern-Simons term for the rifle term. That turns out to be vanishing if you consider the consequence of CPT invariance. The Chern-Simons term for the global symmetries, capital A, they also turn out to vanish thanks to the CPT theory. There's only left the mixed Chern-Simons term between the two, which is determined by certain applications of these, by certain considerations having to do with anomaly. This is a very subtle fact developed by Jensen, Logan, and Yaro, but they have shown, considering some consistence of the Euclidean vacuum of the system and so on, that anomaly should determine all these coefficients. This is a very difficult part, but quoting their works, you can determine these terms. And these are determined by certain mixed anomalies, and the coefficient turns out to be the difference of the two central charges of the 4-dimensional surface, A minus A. The more interesting term turns out to be gauge non-invariant Chern-Simons term, and that should exist. We are dealing with a 4-dimensional effective action in high temperature limit, and 4-dimensional effective action should respect non-invariance under the gauge transformation for global symmetries, which are suffering from two anomalies. So if you make an infinitesimal gauge transformation of the effective action, they should be giving rise to some F-wedge F-time anomalous terms. So it means that in our 3-dimensional background field effective action, there should be some terms which are not invariant on this gauge transformation. And these are all summarized into this gauge non-invariant Chern-Simons term. You can obviously see that they are gauge non-invariant because they are scalars are multiplied in the canonical Chern-Simons density, so the gauge transformation is not zero.
Can you justify this in 4D? You're saying that this is a tofu standard, right?
Yeah,
Gauge symmetry.
Yeah. Global symmetry coupled to background gauge fields.
That's right. Okay.
Can you justify me? Well, for instance, if you have 4-dimensional Lagrangian description, you can really integrate out this heavy colors are prime mode and just derive that.
Yeah.
Even if you don't have Lagrangian description in 4D, you can give an argument that this should be the case. Because this gauge variation of this gives you the desired FHF. There are more abstract arguments, and if you have 4D Lagrangian, you can just integrate out to determine this. But abstract argument really gives the power of this kind of analysis. You can really see the structure of high temperature free energy even for non-Lagrangian theories.
Do you require supersymmetry for this result 5A minus 3C?
Here, I don't think so. Here, yes, I use A maximization here. Yes, yeah. Let's see. But these anomaly coefficient structures should be holding.
Let's see if you are claiming in general.
Okay. Yeah. The general coefficients can be determined, and they are just given by the If it's the general case, you just have to This is a specialization of the general Chern-Simons coefficient, after which I applied A maximization and so on. Before doing that, you should just erase this part and just. There are more general versions of this, sorry, but this is the most specialized result for superconformal field theory, because this is all I need to know. But that's a more general version of that. So anyway, the coefficients of all Chern-Simons terms are determined by anomaly. All you have to do is to plug in the values of our background fields and extract out the divergent contribution of the energy, which turns out to be taking the following form for n equal 1 for higher superconformal field theories. So just like we had 1 over tau dependence, central charge divided by tau dependence for the 2-dimensional particle energy, we have some central charge and some chemical potential dependence divided by omega 1 and omega 2. Both omegas are playing the role of 4-dimensional taus. Since you have 2 taus, there are 2 taus in the denominator. Most simplified case is the case in which the chemical potentials are aligned along the superconformal R symmetry only, because that's the minimum case. And in that case, you have to plug in particular values of chemical potentials, and you obtain the free energies given by the divergent Cardi behavior, and combined with this particular combination of these central charges, 3C minus 2A. It's quite curious formula, that the 3C minus 2A is always positive for interacting with superconformal field theory by a consequence of what is called Hoffman-Maldacena bound. So A over C is between 1/2 and 3/2, and this is what part of the Hoffman-Maldacena bound. And with this positive coefficient given, you should try to Legendre transform to see what is the macroscopic entropy at large charges. And it's a bit subtle. You see complex numbers here and there. So there's a little bit of subtlety in doing the Legendre transform, whose proper meaning has been clarified only recently. I don't have time of explaining that, but if you're interested, I'm going to tell you later. Basically, the rule is to do the Legendre transformation and take the real part of the saddle point in the entropy. To extract out the macroscopic entropy. Anyway, after this, at large charges, one always obtains a positive and macroscopic entropy, supposing that Hoffman-Maldacena bound is obeyed, which is of course true. So that is giving us a macroscopic entropy of a 4-dimensional CFT at high temperature. And this happens to agree precisely with the Beck-Einstein-Hawking entropy of BPS black holes, large-sized black hole BPS black hole in ABS5. So it's a way of accounting for the microstates of the dual BPS black holes, just by anomaly consideration and a little bit of supersymmetry. So let me just conclude. The method I try to explain to you is quite abstract. It just uses anomaly, some abstract uses, to derive the Cardi-like formula for superconformal field theories. With conformal field symmetry only, you have seen that there are many unknowns because conformal symmetry is weak, but a little bit of supersymmetry helps to determine complete either non-trivial high temperature dependence. And I almost haven't used the Lagrangian setup of the original theory, so it applies to many non-Lagrangian CFTs in SCFTs in even dimensions. 4-dimensional non-Lagrangian theories, well, that just applies. The 2-dimensional Cardi formula, you can more abstractly derive using the similar one lower dimensional background field method. It's a background fields quantum mechanics. And that has been elaborated quite earlier by a paper by Juno, Kim, Kim-Young Lee, and Jae-Wook Park earlier last year. Rederiving the well-known Cardi field in a different manner. And most importantly, the technique applies to 6-dimensional CFTs and the dual ADS7 black holes. And I I omit this part because that will be explained by my ex-student Jun Nam-Gong tomorrow. And there are many interesting more directions, and I'd like to finish by emphasizing that what I told you today is just a tiny little bit of story, 50 into 30 minutes, of a more interesting recent advances in GPS black holes and SCFT's higher temperature behavior. So for instance, we have been using these key ideas and more general ideas to count all possible GPS black holes in ADS space higher than 3. So ADS 4, 5, 6, and 7, using higher dimensional superconformal field indices and so on. But this just doesn't fit into 30 minutes, so I decided to talk about a more small story here. If you are interested in the full recent advances, maybe in the next occasion.
Thank you. So we have time for some, excuse me, for some questions, since the speaker used actually 27 minutes.
I used, oh, okay.
Two questions. The first question is how to understand the saturation point for the Hoffman system.
Oh, 3C minus 2A being 0.
Yes.
Well, from Lagrangian field theory's intuition, that's the point where you have only n equal 1 vector multipliers.
Yeah, but in your case, you get 0 and 50.
Look, let's think about this. Let's say we have a bunch of let's say n square abelian vector multipliers. We quickly gauge it. The index is coupling independent. So what will you get? The index for the maximal, the index for the n equal 1 pure superangles theory, which we know is confining. So it's quite natural that the asymptotic entropy is just 0. It's confining theory with just gap spectrum, and the spectrum will be boring, I expect. So the index is respecting the fact, I think, that if you have only vectors, it will be like n equal 1 superangles, which should be confining. That's my interpretation. On the other hand, if you go to the other side of Hoffman-Maldacena, A over C being 1/2, it's just 3 chiral multipliers, and nobody says that the entropy will be vanishing there. So at the other side of the Hoffman-Maldacena bound, nothing special happens to my Hardy entropy. It's macroscopic. Yeah. So only for this vector multiplier bound, I think I naturally find a diminishing, because I think the essence is vector multipliers are making the system, let's say, confining. Yeah,
The second question is, think you argued that whenever there is a four-dimensional of the anomaly,
Yeah.
you will get the three-dimensional transcendence, which represents
Yeah.
right?
Yeah.
That's the argument.
Yeah.
So it's kind of a long inflow but to lower dimension.
Oh yeah. Yes. It's a two star anomaly matching.
Yes, yes.
Sort of.
Do you
Yeah.
have general?
You know what?
Do you have general argument why this?
Well, yeah. The anomaly should be respected even if you just integrate out sort of heavy colors or time modes. That effect should be somehow remaining in this three-dimensional effective action. Yeah. So I was arguing that the gauge non-invariant Chern-Simons term is responsible for that anomaly matching. Even if you integrate out the heavy colors or line modes, the effect of integrating out still leaves some trace in the low dimension effective action to see the truth anomaly. Yeah. It's just natural.
I mean, following the usual anomaly inflow argument, you have some kind of classification.
Anomaly inflow.
Because your inflow equals to one higher, but you go one lower.
Oh, no. The inflow normally deals with defects and boundaries.
Yes.
I rather view it as the UV-IR anomaly matching. Yeah.
Now, if you try to classify the Chern-Simons actions, do you have such kind of classification?
I think it's basically classified. I mean, there are some Chern-Simons terms that I didn't show, including some background curvature and so on, because they are just giving like sub-leading terms or vanishing terms and so on. But I think these Jensen and Logan Yaron's work allows us to determine all the coefficients. Am I right? Yeah.
I'm actually asking some kind of group cohomology classification.
Oh, okay, we can talk later. Okay. Yeah, I'm not sure. Yeah.
Okay, any other brief question? So thank you again.